Hello, everyone. So we'll continue talking about Greens Theorem and its applications. So a couple of comments about your questions or the email last night. So I think Ruben released the scores for the midterm, and there are some questions about it. So please address those questions directly to him because he would know exactly how to respond because he was grading. The midterms, they themselves, they will not be curved, right? So as we discussed before, so we try to avoid curves, and yeah, so I'll look at each of your cases individually once we get all the results in, and then also I saw that in the grades section of the big courses, not all grades are put in, so I'll ask them to put those grades in, so they should appear soon. And so we'll have our quiz tomorrow for about section 15, right, about the double, triple integrals in our usual format. Discussion, yes, yeah, so today, the office hours, yeah, there'll be office hours today, right? So today we have office hours at 2, yeah. as always. Right, and so it looks like we won't be able to cover all the material of section 16 this week, and we'll continue next week, and as well as doing the review for the whole class. But I think once we covered all the material, we just can switch to this discussion mode. So you can email me and ask when you want to have a discussion, and we can have it. Do we have grade bins? I mean, like the brackets for each grade, or what's a grade bin? Yeah, sure. I mean, so right now I think it's between the like 90 plus is A, 80 plus is B, and so on. But often I need to adjust that a little bit. So I have to, what's now in the syllabus. I forgot what's in there. Is it in the syllabus now? So I'm pretty sure I put it every time, but it may not be there now. So yeah. Oh, I didn't put the brackets in. Okay, so but yeah, basically think of it. If you are in the 90 percentile, then it's A, and so on. Well, my impression is that the class is doing pretty good. It's like based on what well, look at the results of the quizzes. Okay. So also, if you list the mean as, yeah, so I'm not sure why they didn't do, so grade scope it's a standard option with grade scope. So ask my TAs to do that for all quizzes. Like once you get all the grades out, you can send everyone the statistics, the standard deviation, and the mean value. Yeah, I asked them to do it, so you should receive those maybe today. Okay. So a quick recap from yesterday. So when we finished with this theorem up on the screen with written in black font. So if you have a vector field in 2 dimensions, PQ, which is differentiable, right? So it means that functions P and Q themselves are differentiable on a simply connected open set D. And I remind you that simply connected means that every loop is contractible, right? So every loop is contractible so that at every step of the contraction, it belongs to the set. And then suppose that the partial derivatives Py is equal to partial derivatives Qx for any x and y, any point in the in this simplest open set, then field f is conservative, meaning that it's a gradient of some function. Now, if the field is not conservative, so yeah, and then the next thing that follows from here will be the Greens Theorem, which says that, well, how about, so what if it's not conservative, right? So then, so if it's conservative, right, then the integral over the loop, over the closed loop is equal to 0, right? But if it's not equal to 0, then we can write the following formula, which says that the integral over the closed loop C, which you can interpret it this way, so that the integral over the closed loop is equal to, of the vector field F, is equal to this left-hand side, right? So it's equal to the qx minus py dx dy. So you can see that if the left-hand side is equal to 0, then, excuse me, if qx is equal to py, then the left-hand side is equal to 0, and we're back to this conservation thing. But otherwise, for any kind of, in general, this is what happens. And then we argue that it suffices to prove the theorem only for a rectangle, because every set, right, on a plane can be represented as at least sort of, which has one component, right? What can also happen, you can have several components, right? You can have set D can be, you know, you can have several components, and then you would need to apply it to every component. But for simplicity, let's assume that there's only one component. So we can cut it into a bunch of rectangles and then take the limit when the size of those rectangles goes to infinity, goes to 0, and this way you can prove the theorem for any set. Now let's finish the proof for the rectangle. So we have this calculation here. So the rectangle has coordinates x0, y0, x1, y0, and so on. And we can break it into four pieces, right? So let's first take care of horizontal parts. So the integral over C1 is equal to integral from x0 to x1 p of t, y0 dt. Integral over C3 is equal to negative integral from x0 to x1 p of t y1 dt. And then if you add them together, right, so we'll get this thing, the difference of these guys, which you can also represent as integral over from y0 to y1 with a minus sign, right, of p of ty dt dy, right? So first you integrate over y, and technically you need to put a different letter instead of y, but that's okay. So first you integrate over y, and then you get this, right? And then that will give you the left-hand side. Okay, and then analogously, you can do that right in different color. So integral over C2 q dy, right, is equal to integral from y0 to y1 q, what's called s, not the other way around, x1 is the same here, yes, x1 s ds, and integral over C4 q dy, it's equal to minus integral from y0 to y1 q, this x1 comma x, right? And this is x0 comma s ds. So integral over C2 plus C4 q dy equals integral from y0 to y1 q of x1 comma s minus q of x0 comma s ds y1, and then which can be written as integral from x0 to x1 q of dy dx q of xx d ds dx. Right. Yeah, and if you combine everything together, right, so get the integral over, so integral, line integral is additive, right? So we have integral over c1 plus integral over c2, integral over c3, integral over c4 of, and then here, if you want, you can also add plus q dy, since dy is equal to 0, and here you can add p dx, since dx is equal to 0 of everything, so p dx plus q dy, which is integral c of this differential form, and by combining these guys, we have integral over rectangle. Let's call it r. It's rectangle r, and we're integrating counterclockwise. Qx minus p y dx dy, which proves the theorem. It's a pretty cool theorem, right? So it allows you to reduce, well, depends how you read it, well, represent a two-dimensional integral with a one-dimensional integral and vice versa. Okay, let's look at some examples. Yeah, the proof in the book, I think it's a bit unnecessary, more complicated. This way it's cleaner. Okay, I think I could not resist to mention differential forms at this stage. So remember we talked about this, I think, during the last discussion, right? So this looks like a one form, right? Because it has a well, sum of functions multiplied by one differential, and that, like the whole integrand here, it looks like a two form. Okay. Now let's calculate using the rules of exterior derivatives of this Durham differential that I showed you before. Let's calculate the derivative, the Durham differential of this form. Right? What is it equal to? So it's equal to, well, it's equal to px dx wedge dx plus py dx wedge dy plus qx dx wedge dy plus qy dy wedge dy. As I explained to you before, dx wedge dx and dy wedge dy are identically 0, and so something's wrong with the order. I'm sorry. Dx dy. So here should be dy dx. Yes. Right, because when you take a derivative and then you multiply it from the left. Yeah, so dy dx, and then if you swap around dx and dy, if you swap this around, you get a minus sign. Right, so this is equal to qx minus py dx dy. So you get it immediately, which means that the Stokes theorem, or the Greens formula, which in this case is called Stokes formula, can be written as follows. So the right-hand side of the formula will be integral over the boundary. So a piece of notation, right? So if C is the boundary of D, then we write it as del, as partial derivative, del D, right? So the symbol means it's a boundary. Boundary of, right? So, and the formula looks like this. If you take one form omega, also let's call this form omega, and we integrate it over the boundary of D. Yeah, so if this is omega, then that is equal to d omega. And on the left-hand side, you'll see how pretty the formula is. On the left-hand side, you have integral of d of derivative of the differential of the omega. That's it, right? So that's sort of the most abstract way to write the formula. Basically, the idea is this: on the left you have differential applied to the form, and on the right you have the boundary, which in a sense also looks like a differential. In some high cohomological sense, it's also a differential. So a formula written in this way is called Stokes formula. Fun fact about Stokes formula that it does not only apply to two dimensions. Omega can be any form of any degree, and in this case, right? So in this case, if it should be, but the dimension of the boundary should be equal to the degree of the form. So, for example, if you have a sphere, right? Sphere is a dimension of a ball. Actually, is the boundary of the ball. So you can integrate, say, two form over the boundary of this ball over the sphere, and the answer will be equal to the integral of the the differential of this form over the whole volume, which will be the free form. Okay. It's not going to be on a test or anything, but I just wanted you to know that there is a very robust approach, which is very universal to those things. Yeah. Questions? Also, in this way, formula is easy to remember. Right? For example, you can say on the test or just anywhere when you need it. How would you know what goes first, qx minus py or py minus qx? Is there any easy way to remember that? Exact, just memorizing. Well, if you are in doubt, you can always do this calculation, right? So what should stand on the left, what should be in the two-dimensional integral is is the derivative, is this exterior derivative of the one form, and you can always do this calculation here, and that will tell you immediately what's going on. Right? So it's qx minus py dx wedge dy. Yeah, it's a very deep mathematical statement. It's it goes into many areas. Okay. So for practice applications, Of course, we can replace one integral by another if we think that the other one will be easier, right? So let's look at an example. Say we want to integrate the following, the form x to the 4 dx plus xy dy over the boundary of a rectangle, triangle, excuse me. So where this triangle looks like this. It's a triangle which is in the first quadrant of the coordinate plane. So it has coordinates 1, 0, 0, 0, 0, 1. Yeah, and it's an integral over the clockwise oriented boundary of this triangle. Okay. Now, and even here, so in practical applications, I recommend, of course, I cannot insist, but to to just do what I just did with the differential, right? So the idea is we don't want to integrate it over the boundary explicitly. We want to replace the integral, this line integral, over by the integral over the triangle, right? So we want to write it as a double integral, right, over the triangle itself of this d omega, and then let's just calculate its derivative, right? So what it should be here, what should stay here is, well, so let's do it in two different ways, right? So this is p, this is q, so it's equal to q x minus py dx dy. That's what the answer should be, but in case you don't remember the order of these terms, which I never remember. Not that I use it every day, I mean, I'm doing algebraic stuff, but if I were you, I mean, whenever I need it, I just take a derivative myself, right? Over this triangle, so we just take a derivative of the form. So we know that here, when you take d of x to the 4th dx, so dx wedge dx will be equal to 0. And then when we take a derivative of y, right? Sorry, we first taking qx, right? So qx is equal to, yeah. Okay, and never mind. So here we take derivative of when we take derivative, so d of x to the 4 dx is equal to 0, right? Simply because dx by dx is equal to 0, right? So it's equal to 0. And now d of q, right? We have y times dx dx dy. Sorry, with a plus sign. Okay, and of course, if you just do it, if you substitute here from qx, you just going to so here this gives you y, and this gives you 0. Either way, you get the right answer. So it's 0. It's integral of y, right? And now we can, for example, integrate through. So we know that this. Let's do an integral. We know that this line is equal to. So it's y is equal to 1 minus x. So first you want to integrate over x. So lastly, yeah, and the first integrate from y from 0 to 1 minus x, and integral of y dy, which gives y squared over 2 minus 0, so it's 1 minus x squared over 2. Which you can write as minus 1/6, right? 1 minus x cubed between 0 and 1. And that's equal to 1/6. Okay, another example with the use of polar coordinates. So say, let's find, using this method, find the area which is enclosed by the ellipse. So we have x squared over a squared plus y squared over b squared less or equal than 1. And let's find the area of this thing. Right. So we know how to write it parametrically. So it's x is equal to a cosine t, y is equal to b sine t. That's the boundary of the ellipse. Let's call it an ellipse E, right? And this is the boundary of E. So what the formula would look like for the area? It's integral over E of 1 dx dy, right? Okay, so and now, so we want to use the formula in a different direction. So we have a two-dimensional integral, and let's rewrite it as a line integral over the boundary. So we need to well, write it as an integral over d of something, some form omega, right? Such that d omega is equal to xy, dx dy. Can we guess such a formula? Can we guess such omega? Well, let's just so clearly it has to be something like which looks like, you know, well, the answer is not unique, right? So we have for example, if we can pick we can take omega is equal to x dy, right? And then here then the omega will be equal to dx wedge dy. Right, or we can pick omega to be equal to y dx with a minus sign, right? And then d omega will be equal to negative dy wedge dx, or it's equal to dx wedge dy. Or there's some intermediate possibility you can sort of split it in half, right? You can pick omega to be equal to x dy minus y dx 1/2. Right, and if you calculate the derivative, you can see it just sort of it's an intermediate thing. So we could 1/2 dx dy minus 1/2 dy dx dy, which is what we need, right? Which is equal to dx dy. Yeah, and we are free to choose any of them, any of these three choices. but the last one, which I drew on the left, looks more symmetric. Right, so let's pick this guy, and you'll see that there will be some. Well, it will the formula will be a little bit simpler. Okay, so the area is equal to integral 1/2 integral over the boundary of the ellipse x dy minus y dx, and then let's substitute the parameterization. So dx is equal to negative a cosine t dt. Dy is equal to b. I'm sorry, sine, negative sine. Dy is equal to b cosine t dt. And then here we'll have a couple of terms. And t varies from 0 to 2 pi, right? So it's integral from 0 to 2 pi of what? X dy, so it's a cosine t times b cosine t minus y dx. So minus cancels, so it's equal to plus a plus b sine t times b sine t times a sine t, excuse me, dt. Right, so this is equal to ab dt. Right, cosine squared and sine squared 1 combined to 1. So it wouldn't have happened if you have chosen the other two options, right? But then you just need to do one more step with the integration. Yeah, I couldn't tell if I was that on A or A. Oh, it's the wedge, right? It's this wedge. It's this inner product of differentials, right? So the wedge product has the rule that dx wedge dy is equal to negative dy wedge dx. So remember when we talked about orientation, right? So the sign was due to the fact that different order of vectors can provide a different answer with the areas and volumes. So the answer is equal to pi ab. Oh, technically you should always use wedge, right? So whenever you see whenever you see an integral, you should, like, since you have a three-dimensional integral, have dx dy dz, it is assumed that it's a wedge product. So most of the calculations that we did say last week, it was not important because after all, more often than not, we just took the absolute value of things, right? But yes, we should always think that it's something that has an order to it. As you can see in Greens theorem, it's really crucial because it allows you to capture the correct placement of signs. Okay. Okay. Can you move to the left a little? Yeah, sure. This way you should have enough room for everything. Yeah, there you go. Right, so we I jumped from well from this line right to yeah, so divergence of that is equal to 1/2 integral over d of x dy minus y dx. Now, one more. So remember last time we looked at this special vector field that came from complex analysis from function 1 over z. So there'll be a continuation of that story. So another example, let's take vector field f, which is minus y over x squared plus y squared, x over x squared plus y squared. And as we discussed earlier, it's equivalent to considering complex valued function f of z is equal to 1 over z and integrating it over a circle. Only not where z is a complex number, which was x plus I and y. So only now let's make one step further and discuss integrals not only over circles but over some surfaces, over some curves which looks arbitrarily. Right? So so say we have a oops. So we show that integral over a unit circle was equal to 2 pi by a direct calculation, right? So we show that the integral over S1 of f dr was equal to 2 pi. Or this is the circle. But now instead let's consider let's consider another contour which looks like this. So it's a contour gamma. And let's ask ourselves what the answer of what will be the integral over gamma of f dr. Right, so this is gamma, and then this is S1. Right, so it's an positively oriented boundary. So you see that between these two curves there is an area. There is a set which is not simply connected, but nevertheless it's a set with two boundaries, right? Let's call it D. And integral. So the boundary of D consists of two segments. So it's gamma union with this S1 inverse, right? Because it's really the boundary should always be so if you define the boundary should be how should I say it? So the orientation of the boundary should be always the same. It should be counterclockwise, right? So therefore, if you are if you are here, right, and you look at how the point on the boundary moves, right? So it goes say from here to here in this direction. So that's a positive orientation. That's a counterclockwise direction. And if you do it for this inner boundary here, I mean, it would go the opposite, right? So it would go, if you're inside, for you it will go counterclockwise. It will go like this, right? So therefore, the boundary of the set is two components, and then it's gamma, and one component is gamma, and the other one is the circle, but only with the reversed orientation. Okay. So think about it like this. Let's take we have an annulus, like, with two circles like that, and then there is a they kind of come close together, right? So the outer circle will be oriented like this, and inner circle will be oriented like that, right? So this way, if you collapse them together, right, you would the orientation will cancel. Does that make sense? So that's why here there's a -1 sign. Okay, so why am I telling you this? Well, I want to use this the Greens formula. So we want to compare integral of this, right? So over so integral over the boundary of d will contain so with the bound, yeah. We want to use the formula, the Greens formula in this way. So integral over d of derivative of this vector field, right, which is qx minus py, right? So we can write this f as a right. So over d, just this area dx dy with so so it has components q and p, p and q rather. I'm sorry. So that will be integral over the boundary of d of p dx plus q dy, and because of this condition here, it will split into two integrals, right? It will be integral over gamma of p dx plus q dy minus integral over the circle p dx plus q dy. And what we'll show in a second, that this integral is equal to 0. So as long as the boundary, this set D does not contain the origin, this integral will be equal to 0, and this will show us that integral over gamma will be equal to the integral over the circle, right? Which would mean that no matter how complicated gamma looks, right, as long as well, it's sort of as long as it's can be smoothly deformed to the circle without intersecting the origin, the integral over this vector field over gamma will be equal to the integral over that circle. So in other words, the details of the path gamma, they are not important, which is something very counterintuitive, right? So normally when you do the integral, you integrate the function over the path, and typically the longer the path is, the bigger is the integral. Not here, right? Because well, of the very special nature of this function. Okay. Is it clear what we're doing? So then we just need to check that the left-hand side is equal to 0. Confused? We'll do a calculation. No, this is what we'll show. Yeah. So we haven't finished yet. Yeah. So it's where we are going. Right. So yeah. Now let's do this calculation. So what is qx? Right. It's the it's the well, minus y multiplied by the derivative of minus 2 oh sorry this that one is this yeah, q is the second function, so qx is equal to derivative of yes, it's x squared plus y squared multiplied by 1, derivative of the numerator, minus x times the derivative of the denominator, which is 2x, right, divided by x squared plus y squared squared. One second, I'll answer that question. So it's equal to minus x squared plus y squared over x squared plus y squared squared. Question: for what inner circle or the top drawing, which direction is going? Oh, yeah. So it's like the so the I think I did the so what matters for the boundary is that the boundary goes like this. So it's clockwise for the circle. Yes. So think of it like that, right? So it's really like you know, you stand here and then you need to watch. Like everything should go counterclockwise. If you look at the point on the boundary, it should move counterclockwise from your vantage point, right? So if you sit if you are in a set, so yeah, like if you're here in point 1, it's what I drew, right? But if you're here at point 2, then both of them will go counterclockwise. So the orientation will flip as you travel from 1 to 2 like that. But the point 2 is not in the set, so that's why that partition is irrelevant. Then when you're outside, say 0.3, then they would both look like. So if you live in the complement of this larger disk, then you would move like that, right? And you would have to flip both of both. Okay. Okay, so that's qx. Then let's do py. It's equal to negative 1, right, times x squared plus y squared plus y times 2y divided by x squared plus y squared squared, which is also equal to negative x squared plus y squared over x squared plus y squared squared, which is the same. So indeed we were right. This is equal to 0. Identically, right? So as long as we don't touch the origin, right? So these expressions are finite. The left-hand side is equal to 0, which means that integral of f dr over gamma is equal to integral over the unit circle of this field for any gamma which can be obtained, which is well, can be smoothly deformed to the circle continuously, right? So which can be continuously deformed to the circle. Which is pretty remarkable, really. It's like it can be absolutely any curve. Provided that it's done continuously. So if you this is the main formula, main computational formula of the complex analysis, right? So in complex analysis, you would have functions that I mentioned last time that say you have some complex function, say r of z, which looks like 1 over z minus a plus 1 over z minus b, say squared, multiplied by something else, right? So one thing you need to worry about, and then say you want to integrate this function over some path gamma, right? Now, definition is very similar to the definition of the integral over the of a vector field, right? With those sign conventions, and it turns out that the answer will be equal to. So you only need to worry about well, so you have point A here, point B, point C, and so on. You look at all those points where you have singularities, right? And then say path gamma is a closed path that goes like this. So it's somehow smoothly hugging those points, right? And so it turns out that what you can do, you can just replace this integral with the sum of 3 integrals like that. And that each of the integrals you can calculate just by, well, essentially the answer for each of those integrals will be equal to, well, 2 pi I, because it's complex analysis, there is an I, and then you will multiply by the coefficient, let's maybe call this z minus a here, let's call this coefficient, say that there's 5 here, right? So here we need to multiply by this coefficient. Okay, so it's a coefficient in front of 1 over z to the minus the Pauli in first power. If you have a second power, so the integral will give you 0, right? So plus 0 and then plus whatever c will get here. So and that's it. That will be like the answer for the integral. So same here. So you asked what is the integral over curve gamma, which is very complicated, and you just say, okay, I don't care how complicated it is, I can just replace the integral of the curve gamma by the integral over the circle. Yeah, it is like topology. So what they're talking, so I didn't want to, yeah, so there's a question, what do you mean by smoothly deformed, continuously deformed? So it means that there is a, well, there is a continuous function which does the following. So it's called homotopy. Okay, so but just, well, the first I just draw the picture and then I say some words about it. Say, yeah, let's do it again. So there's path gamma and then there's a circle here. So it means that there is a continuous process which allows you to kind of contract it down like that. So there's a function, this is gamma, this is circle, that's 1. So there's a function, let's call it h, which does the following. So it's equal to, there's some parameter, let's call it t. Right, you've seen this formula before when we talked about the straight line that connects 2 points in space, right? So when H here, so H here, H will be the family of those curves. So when H is equal, when this parameter t is equal to 0, then the function, then we have gamma, right? And then when H is equal to, t is equal to 1, then H is equal to the circle. And somewhere in between, you have one of those blue curves that I drew. So, so that's the H of some t, where t is between 0 and 1. So this is called homotopy. And if such homotopy exists, so if you can show that you can deform your path, your curve to the circle, then you can replace integral of one by another. So it doesn't always happen in real analysis, just I want to make sure. So it's what happened here was a very special case of the, so it just turned out that this vector field is conservative everywhere except 0. In complex analysis, it translates into condition of that the function is holomorphic, so it's complex differentiable. Of course, in real analysis, what we're doing here, so if you pick arbitrary P and Q and do the calculation, most likely you're not going to get 0 on the left, right? Here we just, well, it's a very carefully chosen vector field, right? So in a sense, once you know P, you can reconstruct the Q and backwards, right? So if you know that dp over dy is equal to dq over dx, it means that it suffices to know only one of them. Yeah. So it's a very special situation here. I get what the proof is. I'm just wondering conceptually, how do I integrals be equal after being deformed? So claim is that integrals will be equal at each step of the deformation. So in this case, if you take this vector field f from above, right, this thing, and you integrate it over any of those h of t, right? So they would still be the same. So it will be equal to integral over this s1. So the way you prove it is basically you would do the same thing. Right? It's a separate theorem. Basically, you can prove it by, well, so essentially the proof is what we just did, right? So you show that you take two neighboring paths. Let me draw a different picture. So there's one, and then there's another, which are very close together, right? So this distance is small, and then you would show that integrals are the same, and then you would make a next step, and then the next step, and the next step, and then you would connect them together. So by induction, you'll show that the first guy is equal to the last guy. Yeah. So I teach this in 185, complex analysis, intro to complex analysis. So yeah, I advise you. Is anybody taking complex analysis in the fall? I'm not going to. Okay, maybe then in spring. Yeah. Okay. So just to summarize, when it happens, right? So, in other words, so if the field is conservative, right? If the field is conservative, then the integrals over this vector field over two equivalent homotopy equivalent paths are the same. So in other words, if one path can be continuously deformed to another path, then integrals are the same, provided that the field is conservative. Okay, good. Okay, let's take maybe a small break and then we'll come back. Okay, so let's continue. Any questions? Our next story is curl and divergence. Yeah, so these are these are two basic operations with vector fields. I mentioned curl in the first lecture of this week. So this is the following gadget. It's defined for a three-dimensional vector field. Although with some ingenuity, you can use it for 2 dimensions. So by treating the third as some spectator. So let F be a 3D vector field in 3 dimensions with components P, Q, and R. It's a 3D, R3 to R3, 3D vector field. So we assume that everything is differentiable as many times as we need. Then curl F, which is also a vector field, is the following, it has the following components. It's dr over dy minus dq over dz, dp over dz minus dr over dx, and dq over dx minus dp over dy. So, which is of course impossible to remember, at least for myself. So that's why we have the following way to understand it. So there's a formal, you should use the formal expansion of the determinant of this 3x3 matrix. So if you take the basis vectors I, j, and k, and then we put, so there's a vector nabla, the gradient vector, which is a differential operator, and it's also a vector, right? So it's a weird object, because you can treat it, I think, as a vector, it has components d over dx, d over dy, d over dz. So it behaves like a vector, but it can also differentiate things if you write it on the left from the symbol. And finally, here you put components of the vector field, and you can see if you evaluate the determinant over the first expanded over the first row, then you'll get exactly what you want, right? So this is the i's component, j's component, and k's component. Okay. So we already see that there's some familiar combination, in particular this one, right? So the last component is this qx minus py, which is of course not accidental. Okay, so so that's what curl is, right? So curl F is the formally is a cross product of the nabla vector times the vector F, and this cross product should be understood in the following sense. So let's take an example. And so we have stick vector field minus y, x, and say 1. Right? What is its curl? Also, as I probably should mention, some books, so if you, especially from those who are from different countries, you might have seen different notation. It's rotor, rot F. So it stands for rotor. So most Russian books and I think some German books, they instead of curl, they use rotor. For North American, we use curl. Yeah, so curl F is, I'll just do the determinant. Yeah, so dx, dy, dz minus y, x, and 1. And you can see here that all derivatives will disappear, right, except the last one, right? So so it will be 0, 0, 2. Right? So we drew this field before, right? So it's a kind of, if you draw it in 3 dimensions, it will look like so like here it has component 1 over along the z-axis, although we could have put 0, right? You could have put any number here. It's true for any, say, so some constant. Let me maybe put 0 here, so it will be easier to draw. Right? It will not change the answer. So on every concentric surface, like in a cylinder, it would look like this, right? It would. It's kind of hard to draw on a pen, but you got the idea, right? So it's a cylindrically symmetric pattern which swirls around counterclockwise. It's like a big tornado, like it's an infinite tornado which spins counterclockwise. And yeah, so curl, in sense, curl, it's with a constant curl, right? So it's in a sense, it's a measure of vorticity, right? It's how much curl, well, the name speaks for itself, right? So how much the field curls in a particular space of in particular place. Yeah, so that's right. So this particular field has a constant curl. Okay. And as opposed to say, if you take a field from point charge, right? Say we take electric field that comes from point charge Q, right? So it's Q over R cubed R, right? Which will have components, it's Q over x squared plus y squared plus z squared to the power 3/2, right? And then components will be well, x, y, z. Well, you can clearly see that if you calculate curl, right, in every when you do this determinant expansion, every component will just cancel, right? So identically, curl E will be equal to 0, which is not surprising because the field doesn't look curly at all, right? It has a a charge, and then there's these field lines, and go away radially, no curl whatsoever. It doesn't have a curl, but it has what is known as the divergence, and that's where we come next. Before we make one more step, and not until after we'll make one more statement, but yeah. So magnetic field has curl, electric field does not. Okay, so there's another important proposition. Claim, right? So if F is a gradient vector field, if this is true for some phi, then curl F is equal to 0. Right. Sort of formally, it's really, in terms of this formal Nabla notation, it's not even surprising, right? Because, well, if you treat this vector Nabla, this Nabla symbol as a vector, you have Nabla cross itself, which is 0 by the definition of by the properties of the cross product. But we actually have to be very careful when we operate with those symbols. So they do behave as differential operators and they do behave as vectors at the same time. So we know there are instances when it's tricky. You have to be very careful. So let's just check this that this is true for as an exercise. It will give us a better understanding of how the symbols work. So of course it becomes immediate if you try to write the determinant. Right, so it's the well, dx, dy, dz, and this is dx phi, dy phi, dz phi. And again, same as with the electric field before, each of the components will be identically 0, right? Simply because each of those 3 minors, 2 by 2 minors that you calculate will have well, proportional columns, so to say. So okay, well, let's do it here. So for I, we'll have well, dy. Well, let's write it with the index notation. So we have phi zy minus phi yz. And then we have a phi xz minus phi zx. And here it will be phi yx minus phi xy. And so assuming that function phi is twice differentiable and the derivative is continuous, then they're all equal to 0. Okay, so curl of the gradient of any function is the 0 vector. Or put another way, if the field is conservative, right, then it has no curl. Its curl is equal to 0. So if the field is conservative, then the curl is not equal to 0. So the counter-positive statement to this will be, if field is conservative, curl is 0. The counter-positive statement, if curl is not equal to 0, then the field is not conservative. So this can be used to check whether the field is conservative or not. Right. So for example, if you have a vector field, so you are given a vector field in 3 dimensions with components x, y, x, y, z, and minus y squared. Question: is it conservative or not? Well, let's calculate its curl. Right, so x, y x, y, z minus y squared so it will be negative 2y minus xy. See, already here there's a problem. It's not equal to 0. But let's just compute it for completeness, and then for k, for j, it's equal to 0 minus 0. Yes, and then for k, it will be equal to yz minus x. So not equal to 0. Not a 0 vector. Yeah. In the vector of the first subscript of first where's psi? There's no psi. Z psi? Phi, you mean above the in previous calculation? Yeah, above in blue. Okay, so in the first subscript of the so those subscripts are, oh, thank you, yeah, good. It should say y. Thank you. Yeah, y and phi are somewhat similar topologically, right? Okay. So this field is not conservative, right? It's rather liberal. Okay. Then the okay, but then yeah. And then we can also get the opposite statement, right? So if we have a field whose curl is equal to 0, and in addition to this, it has continuous partial derivatives, the field has continuous partial derivatives, then it is conservative. Like if f has continuous well, on R3 everywhere, then f is conservative. So it's equal to nabla phi for some phi. Yeah. So that's that's the instance another test. Okay. Good. So the next statement, next object. So we talk about curls. Now let's talk about divergences. So divergence is another formal operation with the gradient vector. Only now instead of taking the dot product, the cross product, we're taking the dot product. So again, say f is a vector field. Now, unlike the curl, divergence can be defined in every dimension. And so let's say f is a vector field with components f1 and so on, fn. its vector field in Rn. Then we defined divergence of f, which is also the dot product of gradient with f, and it's so in Rn with coordinates x1, x2, and so on xn. So it's equal to df1 over dx1 plus df2 over dx2, etc., plus dfn over dxn. Right, or it's the sum goes from 1 to n, dfi over xi. Right, so that's the definition, so in particular in 3D. Right, so we have vector field with components p, q, r, and x3 is given by coefficients x, y, coordinates x, y, and z. Then divergence of f is px plus qy plus rz. So it's a scalar function. Yeah. So you differentiate the first component over the first coordinate, second component over second coordinate, etc., and then you add everything together. That's the divergence. Okay, so let's okay, we're running at the bottom of the page, but I think here we should be able to do the calculation. So let's calculate the divergence of the vector of the electric field of the So the electric field E of the point charge, which is Q over R cubed R. Let's calculate divergence E. Right, so of course it will be easier to do for in spherical coordinates, but let's not do the change of coordinates today. I mean the gradient in spherical coordinates. So what we're gonna do is we take the derivative over x, right, of x or q over here, x over x squared plus y squared plus z squared to 3/2. And the same with y, right? So dy and then dz. So dy of y divided by this thing to the 3/2, and dz over z divided by this thing to the power of 3/2. Okay, so calculate the first one. So we have, let's use the fraction rule, right? So we have x1 multiplied by x squared plus y squared plus z squared to the power of 3/2 minus x times 3/2 multiplied by x squared plus y squared plus z squared to the 1/2 multiplied by 2x, and that divides the thing to the power 3. Okay, so what is it equal to? So we can take out the we can take out the square root, right? So we can cancel off by the square root. So we have 1 over the bracket to the power 5/2, right? And here we get it to it's x squared plus y squared plus z squared minus 3x squared, right? Yeah, let me quickly check if I'm not making a mistake. Yeah, I think that's correct. Yeah, that's right. Yeah, and so like this, right? And you divide by x squared plus y squared plus z squared to the power 5/2. So it's equal to minus 2x. Minus 2x squared. Okay, and now we'll do the same for other components. So yeah, so it's, and then yeah, I'm sorry, we have to actually add them, right? So in Divergence we add those derivatives. So we'll do, so we'll have, so it's q divided by x squared plus y squared plus z squared to the power 3/2. And then it's equal to, well, y squared plus z squared minus 2x squared. And then we add, so the y derivative will be the same, but will be, it will look similar, right? It will look like x squared plus z squared minus 2y squared. And the z derivative will look like x squared plus y squared minus 2z squared. So things looks like it cancels. Just give me a second. I'm going to check it really quick. Oh yeah, that's right. Yeah, I think right. Yeah, I think I forgot. I'm sorry. I forgot one of those things. Right. So here, yeah, never mind. So we have that, right? And then I also forgot the first part. So here, remember, there's also 1. So there's a power 3/2. Yeah, so and indeed, so everything cancels, right? So the what did I do? Oh yeah, that's right. So this is equal to 0, right? Because x 2x cancels this, x is then and so on. So everything cancels out, but so therefore everywhere outside of the origin, the divergence of this field is equal to 0. However, if you actually approach the origin, right? So there is a singularity there where the charge sits, right? And then in sense all the charge density is contained in origin. So therefore, if you integrate, well, it goes a little bit beyond the scope of the course, but so if you integrate this over the volume over R3, if you integrate divergence of E, you're not going to get 0. You'll get actually charge Q, right? It's because although the divergence is 0, this is true whenever x, provided that x, y, and z are not equal to 0. If they are, so you need to carefully evaluate the derivative, all those derivatives at the origin. So you need to take the limit as those derivatives approach the origin, and that will give you what is known as a Dirac delta function. So which will give you the non-zero contribution to the integral. So this formula shows you that in order to find the total electric charge, the electric charge which is produced by which produces this field E, you need to integrate the divergence over the whole space. Yeah, but otherwise here it's in every point it's equal to 0. Okay. So let's look at another example. I'm going to go up the page. Would magnetic field be the opposite? I mean, the divergence of magnetic field is equal to 0. Yeah. So this will be my next. What do you mean the opposite? In which sense it's the opposite? So the magnetic field has no sources, right? So therefore, if you integrate the divergence, the divergence of magnetic field should be equal to 0. Yeah. And here comes our next point, that another claim is that now let's look at the three-dimensional vector field. So let's F be equal to have components P, Q, and R. And then you can calculate the curl. So for every vector field like this, divergence of the curl of F is equal to 0. So magnetic field will be an example because, as I mentioned, magnetic field is always a curl of some other vector. So divergence of magnetic field is equal to 0, meaning that there are no magnetic charges. Okay, so let's prove it. So in other words, it would look like this. It's like nabla dot nabla cross F, right? If you write it symbolically, and again, based on what we know about triple products, the answer should be obvious, right? Because it does look like you can write it as a triple product of nabla, nabla, and F. And because of the cyclic symmetry of the triple product, it's F, nabla, nabla, and it's the same as F dot. So yeah, but basically you have two vectors which are the same, right? And meaning that the volume of this parallelepiped is 0. So it should be equal to 0, but since again those nablas are differential operators, you have to be very careful with using them. So just again, as an exercise, let's prove it more explicitly. Yeah. Well, proving more explicitly means calculating again the determinant, right? So instead of the first row ijk, we need to substitute the components of the gradient, right? Dx, dy, dz, and once again dx, dy, dz applied to f, right? PQR. Right, and clearly you have two equal, two rows of the determinant are equal, therefore the determinant is equal to 0. The rows are linearly dependent. And so divergence of a curl is 0. And so does so is the curl of a gradient, right? So basically, whenever you want to put the symbols together, you can get 0, except when you do the following, except when you calculate the divergence of the gradient. And so what if you calculate divergence of the gradient of some function phi, right? So then you'll get well, let's say we're in 3 dimensions, so phi is just a function of 3 variables x, y, and z. Then that will give you what? If you d over dx phi x plus d over dy phi y plus d over dz phi z, which is also equal to phi xx plus phi yy plus phi zz. And this is also known as the Laplace operator, delta phi. Here, delta is, you can put a delta as nabla dot nabla. So it's formally it's the dot product of 2 gradient vectors, which is the differential operator, which is the sum of derivatives, second derivatives. Laplace operator. So let's summarize, because there've been quite a bit of new information here, right? So that the divergence of curl of any vector field is 0. Curl of the gradient of any function is 0. And divergence of the gradient of any function is the Laplacian, is the Laplace operator of this function. How do we indicate that delta is the Laplace operator and not the change? Well, I mean, you have to infer from the context. Yeah, that's not much you can do about it. I mean, it's often, it's clear. Like when you have, when you write it in the equation, yeah, it should be fairly straightforward. Yeah. Okay, 5 minutes left. Maybe we can try to find the look at the examples of Laplace equation. So delta phi equals 0 is called the Laplace equation. And solutions of Laplace equations are called harmonic functions. And so, okay, Yeah, so so it was invented by this term was invented by French mathematicians who always seek the beauty in this objects. Well, we all do. So let's find some examples of harmonic functions in 1 dimensions and in 2 dimensions. So say in 1 dimension, 1D, right? We have d2 over dx squared. Well, it's only one of them, right? So say phi of x is equal to 0. So any function, so all harmonic functions that are all harmonic functions in 1 dimension are just linear functions, right? If function a is phi is ax plus b, right? Then it's harmonic because its second derivative is equal to 0. Now let's look at 2 dimensions. So can you give me an example of a function of 2 variables whose Laplacian will be equal to 0? So it should be like this. So phi xx plus phi yy is equal to 0. Oscillating spring. Yeah, that's right. So can you write the equation? So that's one of the examples. So it should depend on 2 coordinates, right? So although I think, well, depending on what you're going to write, I think oscillating spring satisfies the wave equation when there's a minus, right? So wave equation would be say phi tt equals phi xx, and here there's a plus. So certainly you can try a trigonometric function, but you can also try some polynomial functions or exponential functions. Yeah, so while we're thinking, I just wanted to make a comment. There's something came up. It would be inconvenient for me to do office hours at 2. So I think I'm going to move them to 3 p.m. So I'm going to make an announcement, and for you guys, you can write it in chat. I hope it's okay. If not, then send me a message and we'll agree on some other time. So you need to invent a function whose second x derivative is equal to minus its second y derivative. Just at least one. You have, so solutions of this equation, they play a role in, they appear in physics, right? So like for example, so if you have, say, 0 here, it would describe the field configuration with no charges, right? If instead of, if in the right-hand side, we replace 0 with some function which describes sources, say you have, that you have electric charge that is placed at this point over here. And then you need to solve this equation. Now it's not a Laplace equation anymore. It's sort of rather, it's called Poisson equation. So it's the Laplace of phi is equal to the source term. If you solve it, it will tell you how, it will tell you the distribution of the field in space. So in the previous example with the point charge, this f of x was equal to q times the Dirac delta function at x equals to 0. So it's a function that describes density. It describes infinite density. So all charges contained at x equals 0. Dirac delta function. Yeah. So it has the property that if you integrate it over 3 dimensions, you'll get 1. It's not a regular function. It is a so-called distribution. It does not behave like a normal function, like a regular function. Okay, we can talk about this during maybe discussion later, but just give me one example of a harmonic function in 2 dimensions. Yeah, so let's see. So if you do Do we actually need the cross term? It's going to work with cross. Okay, so we do second integer. Have 2. Oh yeah, that works. Yeah, but in fact you don't have to. You don't have that. Yeah. So what Han is saying, if you take function phi to be, yeah. So yeah, one of them is x squared minus y squared plus 2yx, which is of course x minus y squared, right? So second x derivative is equal to 2. Second y derivative is equal to minus 2. But yeah, very good. So for that matter, you can even remove the cross term, or you can use it like that. So it's a simple polynomial function which is harmonic. If you do want to go to do some trigonometric functions, you probably need to try something like sine x times cosine hyperbolic of y. Right. So this way. So it wouldn't work with just trigonometric, right? Because you would get the same. You're gonna get minus sign again in both, and then it's not gonna give you the, the minus to kill it. But if you do trigonometric times hyperbolic, that would do. Right. So remember that. Well, derivative of sine, second derivative of sine is minus sine, and second derivative of hyperbolic cosine is the cosine again. So you don't have a sign change. Yeah. So that's also harmonic. Okay. Questions? So yeah, so I think we're almost done with the material. We need to have a couple of, we talk about areas, parametric surfaces. We should probably be able to finish this week, and then yeah, leave the last week for reviews. Or maybe even have a Monday class. We'll see. So the final will be cumulative. You should expect some problems from the last section, from last chapter. Yeah. Yes, that is correct. Quiz beyond chapter 15. We'll have it. Yes, so quiz will be tomorrow. I'll send you as usual, the reminder. It will be only about yeah, double integrals, triple integrals, that kind of stuff. What's an EC? EC? Oh yeah, sure. Yeah, I know that you guys love them. Yeah, so I'll definitely add one. Yeah, sure. Okay, good. So then enjoy the rest of the day, and I'll see you guys tomorrow. Bye.